6. Let's get orientated. Object-orientated. Arrays. All of those things. So far in our episodes, we've taken a very procedural-based look at programming, as in our program always starts at line 1 and goes all the way through to the very end, maybe jumping and changing a bit where we call functions, but generally it follows a set procedure. Processing, and nearly all main programming languages used today, C#, C++, Python, are all what are called object-orientated programming languages. To a greater or lesser degree, it means that they have this built-in function that allows them to be much more user-friendly and coder-friendly from a build perspective. If we use our current program as an example, every time we run it, it makes a box. And when we click that box, if I can click it, it then moves the box's location and re-randomizes and starts typing again. What object orientating would do would allow us to create a class for this box that contains all of its data and all of its functions, and then every time that we manage to click the box, we would then recreate that class rather than moving the box to a single location. This gives us more control when we get to much more complex uses. At this stage, I'll leave it up to you why we would use that and why we wouldn't, but in general, when programming at a much higher level, and maybe not in a creative way that processing is used for, object-oriented programming allows us to control the really minute details of an object without having to recode it every single time we want to make a minor change. For example, every time I click this box, it moves location, but it resets its speed. Using an object-oriented version of this, we could destroy that box and create a new one with a different height, width, and starting speed. We could also do this in code, but we could also introduce color changes and numerous boxes using the same hierarchy of design. This may seem really confusing, so we'll go into an example actually showing what that means. So starting a new processing sketch, we are going to start as we normally do. So we are going to void setup This is the stage that we're normally used to. Object-orientated works in a way that you create a library known as a class that has all the reference data and functions for an item. And to continue the example, we'll use a box. So we create a class for a box, and then in our main program, we create that box as an object, almost like having a blueprint in a manufacturing lab, say a plastic mold on file. And then every time that we want to make an object with that mold, we go get the mold out of storage. So what we need to do is make our mold for the box. To do this, I'm going to create a new tab using the drop down arrow above. I'm going to call it my box. Now normally, in the procedural method of programming that we know, my box never gets called because we never reference it at all. So what we need to do is create an object and then tell our object to go into this class tab to receive all its information. To further explain how a class and an object work together, we're going to create a program as we normally would. So inside setup, I'm going to give it a size of 500 by 500, and in my first line of draw, I'm going to tell it to set it to a black background every time. So now I have a sketch that draws a black box with nothing in it. First thing we're going to want to do is create the variables for our box, and in this case we're going to need a float for x position, y position, speed and size. We don't need speed. just size. Let's make these global. In setup, we are going to set all this information, so we'll do int random x position is equal to int random width. Our y position is equal to int random height, and our size is going to be equal to, let's say, int random 50. So now we make variables, we give them random values. Next, the last thing we need to do is draw our box. Run it, and we'll see every time that we run the sketch, our box is made at a random location somewhere in the panel. Now that we've done that, what we can do, we turn all of this information into a class and then create that class every time the program's run. We can reset all of this information, still using it in a setup way, without needing to stop and start the program every time. So, in my box class, I'm going to go over there and I'm going to declare it as a class. And I'm going to call it box. And just like we would with a function, we need to set it all within curly brace. And then, like we do out here, we need to take all these variables and set them. So I'm going to cut this, and I'm going to paste it. And then we need to make a function to actually draw it. So I'm going to make a new void draw. And then I'm going to bring in this part here. And we can also get rid of these variables because we don't need them anymore. So now if I run it, nothing will happen because we need to tell it how to redraw this box from a class rather than drawing it in line. So the first thing I'm going to do is I'm going to tell processing that we're making a class. And I'm going to call it box. So we're going to make a class called box, and we're going to tell it that the information for it is in my box. So now we have class box, and in our program, that class is going to be referred to as my box as well, just to keep it simple. Instead of setting all the variables, all we need to do is tell processing to generate a box. So I'm going to do my box is equal to new box. So that simply says we've made a my box class referencing the box class in here. In setup, we are telling processing to create a new box, so it's going to create an object based on this information. So we'll generate a box with an X, a Y, and a size. The last thing we need to do is tell it to draw it. So I'm going to tell it to reference my box dot draw. And what this is going to do is it's going to look to where the my box class is, which is box, look for the draw function, and then operate what's in there. So instead of procedurally going down and then say referring to it at the bottom of a project, we're just telling it to go and look in this tab for all that information. And now if we play, you'll see that we generate a box. And every time we stop and run it, it'll operate just as it did before. We can also add back-end interactivity like we're used to. So if I had a mouse press function, and then I tell it to, let's say I want to regenerate the box's information like this. So instead of in setup, I'm going to copy this, paste it into pressed, and now every time I push the mouse, it's going to re-randomize or rerun the myBox variable information. So if I run it, every time I click the mouse, it's going to create a new instance of that box. Whereas with our main program, every time that we clicked the box to score a point, it would then move that box and give it a new X, Y, random height and width, all based on our code. All we'd need to do now is tell it to regenerate our box with new information. It has roughly the exact same functionality, but it does it with almost half the amount of code in a much cleaner way. As you can see, our main program is only 16 lines, and our box code is only 12. We are missing a bit of functionality, such as the movement and the checking bounds, but you can see how it's easy to keep track of your program in a much easier way. Objects can be much more complicated than that, and they can use something called inheritance, where they receive information or variables from the main program or another object to drive them. We haven't explored that in this, but we can make some quick changes to actually do it. An example of this would be if we remove our variables from the main program and put them back into setup. What we need to do now is work out some way to pass these variables into box. So we would do same as with any function, xpos, ypos, size. So now we have global variables that can be changed anywhere in this main program. During setup, we create those variables once, and then we create a new box with those variables. So now, in our box, same as before, we need to reference the variable, but now we can make the box inherit that information. So inside my class box, I'm going to specifically code the object's inheritance information. So, like a function that's receiving information, I'm going to create variables called temp x, float temp y, float temp size. And then here we do x position is equal to temp x, y position is equal to temp y, and size is equal to temp size. To avoid confusion, these variables here have no relation to anything on this page and vice versa. They run as two completely individual processing sketches essentially. All we're doing is telling this line of code here tells our program to go into this other file and receive the information. That is where the inheriting comes into play. And this can be quite powerful because you can have completely dynamic objects that are based on real information in your sketch. As we go on with this tutorial, we'll see how we can use that dynamic effect. So now, every time we run our program, it will still work the exact same, but our variables are being made in our main patch and then inherited by the object at the time of creation. An example would be if we randomize these every single time, and then I print, for example, x position, you can see, let me put that on a new line for clarity. You can see that the value of x is constantly changing, but our box is not, because it inherited the value of x at the time of its creation. If we were to reuse this line of code here and redraw our box, every time the mouse was pressed, we can see it would still change as it did before, but now it's using the values it's inheriting from the main program to control itself. This can be really powerful. Associating it with a real life example, let's say our class was telephones, but then every time that we created a phone we wanted to make it match a different style. Each phone has a different size, width, specification. We can have variables for that set up in our class that we then pass, and it inherits from the main program, allowing us to have what we call children, all based off the same parent, yet each in their own way slightly different. Now that I hope we have some basic understanding of what a class is and how it can generate objects, we need to look at how we can use that in the scope of actual programming, because being able to have one box that we can regenerate over and over again isn't particularly useful in the grand scheme of things. Now that we can write classes and build objects from it, we can make an entire array of objects based on a single class. And this is where object orientation takes us beyond the usage of programming that we've had already. For example, we'll look at arrays in detail in the next episode, but before we continue we need to understand what an array is. An array is simply a block of information that we want to allocate together. The most basic concept of an array is it is a storage container for whatever we want to put in it. Rather than a variable which holds one piece of information at a time, an array can hold multiple variables at once and then be looked at or iterated whenever needed. For example, this is a 1, 2, 3, 4, 5, 6, 7 slot array that has 7 digits in it. And if we were to reference this array at slot 3, we would receive a different variable than if we were referred to it as slot 1. We can do the same with objects. So I'm going to make a new processing sketch, and this one we're going to do very much the same. So we are going to do void setup and same as before, we are going to make a class. I'm going to call it boxes. And then in the exact same way as before, we are going to do class boxes I'm going to give it a float x position is equal to int random width. So the exact same as before. I don't need to do anything in terms of inheritance. We're not going to pass in again at this moment. I'm going to draw it. We know that if we did boxes is equal to new box boxes dot draw. Oh, called it wrong. So this is boxes box my boxes boxes is equal to new boxes, and then it should be boxes. So this is us at the exact same stage we were before. Every time we run it, it'll make a new box. What we're going to do now is create an array of boxes. So we're not only going to hold one, but we're going to hold multiple. Each of them generated randomly every time that we start. So instead of creating a single class, we're going to create what's called an array list. An array list is simply a programming variable for a number of objects in one place. Instead of boxes, we're going to array list. We're no longer going to draw it like that. So now we declare our array list of boxes, we create our array list of boxes, so the program will run. It's just missing the draw section. So now we can create any number of boxes we want, but before we can visualize them, we need to actually create the array and load it with objects. Right now it's just nothing. It has no defined length or end. It doesn't exist. So we're going to use a for loop to create and limit the size of our array. We're going to do loop is equal to 0. Loop is less than my boxes dot size. Loop plus boxes b is equal to boxes my boxes dot get loop. So in the first line of our loop, we're telling it to go into our boxes array and get that index. So for example, in the first loop, it will load the my boxes array index 1, and in the second loop, it will open my boxes index area 2. So 3810, for example, until it reaches the last one from the end. And because arrays work on a 0 base, when it reaches the size, which in this case is 7, it will go on too far. So we need to be less than 7 for it to still be active. So it'll loop through and it'll be 0 is okay, 1 is okay, 2 is okay, 3 is okay, 4 is okay, 5 is okay, 6 is okay. It's now, the loop is technically 7, and as 7 is not less than the size of boxes, it will then terminate. Now we've got the array, we can do things with those objects. Most importantly, we're going to actually make them. So I'm going to do b.draw, and then I'm going to end the loop. Loop is already ended. I've also just realized we haven't actually added any boxes to our array. So I'm going to create one. So I'm going to do my boxes.add new boxes. So now setup creates our array list and then adds 1 to it. So now our size is 1, so it means it'll reference index 0, run it, we should see a box randomly generated every time. Yeah, that's the mistake I was making. So what I can do now is I was to duplicate this message. We'll get 2 boxes every time. But we're trying to make code less for ourselves. So I'm going to delete these. I'm going to do an int called limit is equal to 20, and then I'm going to do for int I is equal to 0, I is less than or equal to limit I plus plus So now every time I run it, it will create 20 new boxes every single time. All indices are all separate entities of the box's class. So every time that we create a box, it gives it a random size, a random width, and a random location within our space. We could jazz this up a little. RGB float int r is equal to int random 255. Make that 3 times. Run it. So now every time that we run the program, each of our boxes will be given a random red, green, and blue color. But all of these are made of the same base, so they're all still a single box technically that we've just changed the parameters of during generation. In our loop, I'm going to make it a bit more exciting. Or in our draw, I'm going to make it a bit more exciting. Void mouse pressed my boxes dot add new boxes. The best thing about an array list is it's dynamic, so we can change or expand the size of it at any time we want. And you can see this by there's at no point we've ever set a limit to the size of an array list, like we would normally need to do with an array. And that's the reason that arrays is the next section, as this introduces it without all the confusing overlying control methods. An array list is completely dynamic inside memory. So what if I run this and click mouse pressed, it's going to let me add an infinite amount of boxes until the computer runs out of memory. So we'll add a quick limiter here. If my dot boxes size is greater than 20, then something, and I'm going to tell it to my remove 0. So every time that we try and add a new box and my boxes already has 20 or more items in it, we're going to tell it to remove the first index, aka the oldest box. So every time it'll remove 0 and create a new slot, and everything will move down 1. Like this is called pushing and popping, but we'll come onto that more in the next episode. So now if I play, every time I click, you'll see that a box disappears as a new one's created. Yet, it's in no way the same as the box before it. Let's get a bit more exciting and add some movement. So I'm going to add a b.move section here. Thankfully, in our time and processing, we've built up quite a library. If we load up our main program, we have done some good work in terms of the movement of our box. Every time that it spawns, it moves, and every time we click it, it resets the movement information. We can use this as a reference, so we don't need to retype it. So, what do we want? We want our box move information. I'm going to paste this in. and then it's called move box is the function. If we try and play it, you'll see that extra doesn't exist, and that's because that's the boolean we use for our checking bounds. So I'm also going to add check bounds. And I'm going to create our boolean extra wider, and then we'll also need the part that controls that. We're no longer going to change the movement speed because that's just unnecessary for now. That's the part that slows the movement speed down over time. Now if we run it, movement doesn't exist. We're going to add an integer movement is equal to 5. Box W and float box height are equal to so we can tell that's not properly checking bounds. So we want to add that every time the box is moved. So we'll do check bounds. And there we go. We have 20 different instances of the same box, all referencing the same chunk of code, just independently. So every time, if we watch this green one here, it reaches the top or the edges, it runs the check bounds command, and if the check bound command proves to be true, it bounces back in the right direction, completely without interfering with any of the other boxes in existence. And this is the true power of object-oriented programming. Otherwise, we would have need to type out all of this code 20 times just to achieve this result, even with the mouse press interactivity. We have a multi-character game in existence where each of these boxes could grant you a different score based on its size and width. In this episode, we're not going to change our main program, as it's not really necessary, and it will be more of benefit after the next array-based learning. So right now, instead of interfering with our reference, we're going to save a version of this file, save as, my program for people, episode 6. We're going to call this multi-object orientation, and we'll see you in the next one.